You ready?
Yes, ready when you are.
Very good. So it's a pleasure to continue the session with Sam Collingbourne from the University of Edinburgh, and he will talk about uniform boundedness for linearized gravity on black holes from the canonical energy.
Thank you very much, Mihalis, for the introduction, and thank you for the invitation. I'm very sorry I'm not there in person. Hopefully soon I will be able to travel a bit more again. So as Mihalis said, we're going to give a techniques talk and try and promote the use of canonical energy for linearized gravity. So I'm going to talk about obtaining estimates for linearized gravity on black holes from the canonical energy. So let me give you a brief outline of my talk. So I know there are many experts on the stability problem in the audience, but for clarity, I'll give a very brief review of the black hole stability problem. I'll then introduce the main technique protagonist for the talk, which is the canonical energy, and talk about conservation laws or the problem of conservation laws for linearized gravity. I'll then introduce the spacetimes that are going to be the main spacetime protagonists for this talk, which are uh, Schwarzschild in four and more dimensions and the Reisner-Nordström spacetime. Now the results I present will be in double null gauge, so I'll give a brief review of linearized gravity in double null gauge and talk about how one gets a coercive estimate on four-dimensional Schwarzschild from the canonical energy in double null gauge. I'll then talk about recent work um, with Marius Apatroai and Elena Georgi on Reisner-Nordström and talk about some work in progress for the Schwarzschild-Tangerlini case or n-dimensional Schwarzschild. Okay, so in general relativity, we work with an n-dimensional smooth Lorentzian manifold, and we require the metric to satisfy everyone's favorite equation, which is the Einstein equation. So this is an equation relating the curvature of the Lorentzian manifold to a matter model that one has to input by hand. So one can set this energy momentum tensor for the matter to zero to get a non-trivial theory because of the nonlinearities of the left-hand side, and this is known as the vacuum Einstein equation and reduces just to the Ricci flat condition. In this talk, I'm going to be interested in one other matter model, which is electromagnetism, which has an explicit energy momentum tensor constructed from a two form given here at the end of the slide. Okay, so the type of equation that the vacuum Einstein equation is obscured by diffeomorphism invariance, but it should really be viewed as an evolutionary equation, and you can see this in harmonic coordinates. So if you require your coordinates to satisfy that box equals zero, then the vacuum Einstein equation has the form of a system of quasi-linear wave equations. And it indeed admits a well-posed initial value problem. So if you give me uh, initial data for the vacuum Einstein equation, you get a unique maximal spacetime up to diffeomorphism invariance. And this was shown in the monumental work of Choquybreha and Garrosh in 52 and 69. And this is the proper setting to talk about stability because the nonlinear stability question should be stated in the following form. So if you give me a known solution, then I can ask whether a small perturbation of the initial data for that known solution um, does the resulting spacetime, which I get from this well-posedness theorem, remain close to or asymptote back to the original spacetime. If so, we would say the spacetime is non-linearly stable. If not, we would have the presence of an instability. This is a very difficult question to address, so a good first step is often to linearize, and all the results I will state today will be in this linearized setting. So, what is the linearized vacuum Einstein equation? Well, it results from formally expanding the Ricci flat condition by adding a perturbation um, this epsilon h, where h is a symmetric 2 tensor here, and formally expanding the Ricci flat condition to order epsilon. And at order epsilon, you'll get this equation for h. So it couples to the background geometry through the connection for the background and the Riemann tensor here. Okay, and here we have the wave character coming through um, if we write this as a box. Okay. So for a linear stability statement, we aim to prove that any solution to this linearized vacuum-Einstein equation that arises from suitably regular initial data obeys energy bounds and decays sufficiently fast. Then we might have some hope of addressing the nonlinear stability problem. Okay. So how does one how does one get energy bounds typically? So these typically arise from um, applications of the divergence theorem to currents that one constructs. So if you have a theory on some space-time background, you can often construct some conserved currents when they're divergence free. So a natural construction is if you have some theory that has an energy momentum tensor, you can contract it with a vector field on the space-time. Now, this will be divergence free when the vector field is killing. Okay? And very formally, one then can obtain energy estimates and indeed conservation laws from applying the divergence theorem to a space-time region bounded by, say, two homologous hypersurfaces. So you would end up with a potential energy to the future, potential energy to the past. Sorry, energy to the future, energy to the past is equal to a space-time bulk. And from this, one can start to derive conservation laws in the case of a vector field that's killing and potentially energy estimates in the space-time bulk when it's non-killing. Okay, so for example, if you take the wave equation on four-dimensional Minkowski with the killing field associated to stationarity, you have a conserved energy computed from which you can compute from the energy momentum tensor for a scalar field. So you end up with this conserved energy for all the derivatives on, say, a t equals constant hypersurface. Okay. The issue for linearized gravity is that there is no energy momentum tensor. And this essentially boils down to there being no local notion of gravitational energy momentum. You can always take a frame, or you can always take a set of coordinates locally, your normal coordinates, and set the Christoffel symbols to 0. So what's the way around this? Well, this is where the canonical energy comes in. So I'm going to try and motivate this with a simple example with the wave equation and then move on to the more complicated example for linearized gravity, since the expressions are a lot more involved. So suppose I have two solutions to the wave equation. Then I can construct a divergence-free current using a symplectic form on the space of solutions. So you can check that if phi and c satisfy the wave equation, then this current here is divergence-free. However, this involves two solutions. So if I wanted to get estimates on a single solution, what I could do is plug in for phi the Lie derivative of c with respect to a killing field, since the Lie derivative commutes through the wave operator. So this is still divergence free. So let's do a small computation together. So if I do this computation and I plug in this solution, which is the Lie derivative of c with respect to x, and then I expand here with the definition of, I just expand the Lie derivative and I distribute the covariant derivative over the vector field. I end up with two terms here, which I can then produce a total divergence from this term here after, no, I apologize. Sorry, I can produce a total divergence and use the fact that x is killing to swap the um, indices on this vector field, this relation here, um, to produce a total divergence. And what I can, sorry, what I can produce in the end is that this current here is equal to the energy momentum current that we can construct from a contraction of the energy momentum tensor into X and the divergence of an antisymmetric 2 tensor. Now this here is always divergence free, since if I apply another covariant derivative to this and then use the infectious nature of antisymmetrization and then the Ricci identity, this term is always divergence free since you have the contraction of, in the end, the Ricci tensor into A. So then you have that this current here, when we use the Lie derivative of C in the current, is essentially, of the total divergence, the standard current that you get from the energy momentum tensor. Okay, and this is the sort of structure that goes through um, to the canonical energy. So you don't have an energy momentum tensor for linearized gravity, but you do have a current which is based upon symplectic structure. So it turns out that this current here, where P and H are solutions to the linearized equation, and this capital P is just a combination of a particular combination of inverse background metrics. This is conserved when P and H solve the linearized equation. So to start getting a current and doing energy estimates from a single solution, what one can do is the same trick where one plugs in that P is the Lie derivative of H with respect to X. And at this point, you might start to obtain a useful conservation law. Okay. However, one of the major issues with this is that when you look at these energies, and I take an extract from Hollins and Wald's original paper on the canonical energy in 2013, um, the coercivity of this object is opaque. Um, so it's not clear whether one can actually obtain control of a norm from the canonical energy. Okay. One other slight um, slight annoying thing about the current form of the canonical energy is that if you plug in that P is the Lie derivative of H with respect to X, you end up with second derivatives in this term here. So it doesn't look like a natural energy norm that you would control. You can indeed modify the canonical energy to get something that's a little bit more natural, um, which is this current here. So if you are bored in my talk, you can check that this current at the bottom of the slide is indeed divergence free. But this indeed just has first derivatives appearing in the current. So on each, if you evaluate this on a hypersurface, you will just get first derivatives. So it starts to look a bit more like a natural energy that that appears. Okay. So I'll give a slightly alternative viewpoint on the canonical energy, but I'll try and review the 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 Hollins and Wald stability criterion. So the canonical energy arises originates from a work of Friedman, but was really popularized in 2013 by this work of Hollins and Wald, and they built a stability criterion based upon the canonical energy. So they took this current and evaluated it on Cauchy hypersurfaces and really came up with a criterion based upon its sign whether a spacetime was stable or unstable. So for a class of immiscible initial data, and this means that there's no perturbation of the ADM parameters, the linearized constraints are satisfied, there are certain gauge conditions that they're baked into this for finiteness at the horizon and null infinity if one is on a black hole spacetime. And there's a condition of being an axisymmetric perturbation if you're in a rotating spacetime. We have this condition that positivity of the canonical energy is an indication of stability. In particular, you can read off from this that you should be modally stable. Negativity, however, is an indication of instability. And the argument um, can be viewed in the following manner. So a negative canonical energy implies that a certain modification of it is also negative, and if one is dealing with axisymmetric perturbations or is dealing, axisymmetric perturbations of a rotating black hole, or is dealing um, with a non-rotating black hole, then you can show that the flux of this modified canonical energy is positive through an event horizon and null infinity. So if it's negative initially, it can only be more negative. So it has a nice monotonicity property, and this prevents this is an obstacle to stability. Okay, so I'm going to try and tell you about some more successes in my own work later in the talk, but let me outline some successes from the canonical energy from some previous works. So in the original paper of Hollins and Wald in 2013, they showed that the canonical energy was negative for many black string spacetimes. So in particular, the Schwarzschild black string. Um, so you can infer this as a proof of the existence of a Gregory-Laflamme type instability. There's also the work of Hollins and Ishibashi in 2015, which addressed a conjecture of Durkee and Real for higher dimensional black holes. So they showed that the canonical energy was negative for a class of extremal rotating black holes in higher dimensions. So for some class of Myers-Perry, for example, this theorem applies. There's also the work of Green, Hollins, Ishibashi, Wald in 2016, which showed that the canonical energy was negative for linear perturbations on asymptotically ADS black hole spacetimes, which exhibit superradiance. So this is of relevance, for example, to Kerr ADS. And then there's this work of Prabhu and Wald in 2018, which showed that if you construct a metric perturbation from a Hertz potential, which is a way of producing a metric perturbation from solutions to the Tchaikovsky equation, you get a positive canonical energy. And this is on Schwarzschild. Okay. Now the theory of canonical energy, as I've outlined here, was in vacuum. However, it's been extended and to modified theories of gravities by Joe Keir in 2014. Okay, so let me introduce now the spacetimes of interest in my talk. So this is the Schwarzschild-Tangerini spacetime. So this is an explicit solution to the vacuum Einstein equation, where I've written the metric in its traditional form. So this is typically viewed as a one-parameter family of massive black holes, where this is the metric that would live on the exterior region. So we have a parameter m, which we interpret as mass. This notation here for this slashed gamma is the notation I use for the standard metric on the n-2 sphere. We have a coordinate degeneracy at r equals 2m to this funny power, which corresponds to the future event horizon. We have a curvature singularity at r equals 0 when we suitably extend. The solution is static and hyperspherically symmetric. So we have a notion of time independence. And it sits as a subfamily of the Myers-Perry family of black holes, or the Kerr family of black holes in 4 dimensions. You can draw a Penrose diagram, which I will use heavily later in this talk, for the maximal evolution of Schwarzschild initial data. Here I've drawn the two-ended version. So here we have an exterior region in light gray, which is bounded to the future by an event horizon, across which is a black hole region, which terminates in the curvature singularity at r equals 0. Note that every point in this diagram is now an n-2 sphere. Over to the right, we have this Scry plus, which is future null infinity, where you should think of as idealized gravitational wave experiments taking place. You can read off causal relations in this diagram by plotting light cones upright, and you can see that you can consider the stability of the exterior region independently of the interior of the black hole, as the interior does not affect the exterior of the black hole. So I can really talk about the stability of the exterior of Schwarzschild, which is going to be of interest later in the talk. Okay. So the other protagonist of the talk is the Reisner-Nordström spacetime. So this is an explicit solution in 4 dimensions to Einstein-Maxwell. Here we have a modification of the Schwarzschild metric with this q squared over r squared term. And we have an explicit Faraday tensor which is generated through a one form, which I've given here in A. So we have a 2-parameter family where the m is as before is the mass and q is interpreted as the charge of the black hole. We have a coordinate degeneracy at r equals r plus, which corresponds to the future event horizon. We have another root of the horizon polynomial here, which is r minus, and this corresponds to the Cauchy horizon and is the end of the maximal future development of Reisner-Nordström initial data. The solution is again static and it's spherically symmetric, and it's now a subfamily of the Kern-Newman family of solutions, which I think Elena will talk about later in the conference. Okay. So having talked about some previous work on the canonical energy, let me talk about some previous work on the stability problem. Now, there's a vast literature on this stability problem for the Schwarzschild black hole, so I apologize already for not mentioning everyone that should be mentioned at this point. I'm going to highlight some works that are of particular relevance to the results I'll talk about later. So in 4 dimensions, the study of the stability of Schwarzschild dates back to the work of Reggie and Wheeler in 1957, who looked at mode solutions to the linearized equation. This was continued by Zerilli and Vishwesvara in the 70s, but the full linear stability result was resolved in 2016 by De Firmus, Holzigel, and Rudnansky, and this was done in double null gauge, which I will employ today. Another work that came alongside this was a work of Gustav Holzigel in 2016, which studied or produced conservation laws and coercive estimates from the system of linearized gravity in double null gauge, as presented in De Firmus, Holzigel, and Rudnansky. And this is really the inspiration for most of the work that I'll present today. Then in 2021, we have a resolution to the nonlinear stability of Schwarzschild by De Firmus, Holzigel, Rudnansky, Taylor, which is a stability result without symmetry for the full expected set of perturbations. On the Reisner-Nordström side, we have the result of Georgi in 2020 for the linear stability of Reisner-Nordström when Q is less than M, so in the sub-extremal range. And then there is the result of Aperture I in 2023, which produces stability and instability result for the Tchaikovsky system when at extremality for when Q equals M. And I think Marius will talk about this later in the conference. For higher dimensional Schwarzschild, there's a lot less known. There is a mode stability result of Ishibashi and Kodama in 2003, which uses a decomposition into vector, tensor, and scalar harmonics on the m-2 sphere to produce master equations. There's the work of De Firmus and Holzigel in 2010 in symmetry and 5 dimensions, and it's a nonlinear result. In 2013, there's the result of Volker-Schlu, which produces a boundedness and decay result for scalar waves on the background in arbitrary dimension. And in 2018, there is a linear stability result for the master quantities that Ishibashi and Kodama studied. And this is uniform boundedness and decay for these master quantities in dimensions less than 6. So the results I want to present are all set up in double null gauge, so I'm hoping to at least give you some nodding familiarity with double null gauge going forward. So double null gauge is a set of coordinates such that the metric just takes this form here. So we have coordinates u, v, and these theta a's. The level sets of u and v are null hypersurfaces, and these level sets intersect in n-2 spheres. This G slash here is the induced metric on these surfaces, and this B is a vector on these surfaces. It can be viewed as the null lapse, if you like. This omega is a function on M. Sorry, the null shift, and this is the null lapse. I apologize. So this is a function on the manifold. Okay, so what is the idea of double null gauge? Oh, sorry, I'm getting ahead of myself. Let me give you an example. So an example of double null coordinates is on Schwarzschild, on Schwarzschild is the Eddington-Finkelstein coordinate. So if you introduce a tortoise coordinate as so through this differential equation here, this prime is differentiation with respect to r, you can define this u and v as this combination of t and r star. This produces a metric you can check explicitly in double null form with a vanishing shift and a null lapse of the usual Schwarzschild factor with the rescaled r. Your level sets intersect in two spheres of radius r, and your induced metric on those on the two spheres is the standard n-2 is the standard metric on the n-2 sphere. Okay, so what is the idea in double null gauge? Well, it's to decompose your connection and your Weyl curvature with respect to a null frame. So you define an E3 and E4, which are null vectors. If you plug them into the metric from 2 slides ago, you'll find that they're null vectors, and you have a local frame on these n-2 surfaces. And you decompose the connection, the Weyl curvature, to produce tensors on these surfaces. So for example, you can decompose the connection to produce the shears, these chi and chi bar, and you can decompose the Weyl curvature in the following way, this alpha and alpha bar. And these, for those who are unfamiliar, are the variables that correspond to the Tchaikovsky variables in the Newman-Penrose formalism. So how do you encode the Einstein equation in this formalism? Well, you decompose the Levi-Civita conditions in this frame, and you decompose the definition of Riemann curvature also in this frame, as well as all the Bianchi identities. So you end up with a huge amount of equations, but for analysis, that's usually pretty good. So after decomposing and linearizing around Schwarzschild times Giorlini, this is half of the equations. I'm not expecting you to take any of these in, but you can see that some of the Levi-Civita conditions are sitting up here. Some of the Riemann tensor definitions, the definition of the Riemann tensor are decomposed just sitting down here, and here over here are some of the Bianchi identities. Okay. Now, sitting in this complicated system of equations is actually a decoupled subsystem. So, which actually governs the dynamics of linearized gravity and is gauge invariant. So this is the famous Tchaikovsky, well, here, system of equations, but in 4-dimension Tchaikovsky equation. So this is in arbitrary dimension at the moment. You have a coupled system between these alpha and alpha bar and this tau hat, which vanishes in 4 dimensions. So you get a decoupling of this alpha and alpha bar equations. So these equations here are not my own. The n-dimensional case dates back to Durkee and Real in 2011 and Godgazar, but in the 4-dimensional case it dates back all the way to the 70s, Bardian and Press, Tchaikovsky, and then Ryan, also in 74. So there's a few issues with the Tchaikovsky equations. First of all, is an issue already in 4 dimensions. There's no known conserved energy at the level of first derivatives of alpha. So that's a problem from the point of view of trying to do energy estimates. In the Firmus-Holzhauer and Rudyansky from 2016, this was solved via what's come to be known as the Chandrasekhar transformation, which is a second-order differential operator applied to alpha or alpha bar, which takes it to a wave equation with positive potential, which does have conserved energy. The issue in higher dimensions, as you can see already, is that decoupling fails um, for the Tchaikovsky equation. Um, and this is happening even on highly symmetric spacetime. So here I've linearized around Schwarzschild-Tangellini. It's already a coupled system. I think in this work of Durkheim Real from 2011 that I'm citing, they show that you only get a decoupled Tchaikovsky equation on spacetimes that are Kund. Another problem is that there's no known Chandrasekhar transformation for n greater than 4. So one has to think about alternative methods or hope for some transformation um, to address this problem. So I'm advocating for the former. Um, so this is where the canonical energy comes in. So the idea is to avoid the use of um, special transformations and the special decoupling, and really admit that linearized gravity is a system, and the canonical energy produces a conservation law for this system. The problem with it is that the coercivity of it is opaque, so controlling a norm is difficult. However, there is some guidance from this work of Hosegel in 2016, who spotted remarkably by eye a conservation law for linearized gravity around Schwarzschild. Um,
Sam, can I ask a question?
yes.
Sorry to interrupt. Yeah, what's the status on mode stability for that system in all dimensions?
Um, so that was solved by Ishibashi and Kodama
It's
for
included in the work for all dimensions?
for the Tchaikovsky system. I don't
Yeah.
know if that's been done. That was done it was done from the point of view of linearized metric perturbations.
Thanks.
Are there any other questions? No. Okay. So right. The idea is to admit that linearized gravity is a system and try and deal with the coercivity property. And we have this guidance that comes from Hosegel's work, who spotted remarkably by eye a conservation law for linearized gravity. So in this system of equations, he spotted that you could construct a conservation law. So what's crucial about this is that he also managed to derive a coercive estimate from this, and I'll talk more about this later. But this gives one hope, if connected, that one could produce coercive estimates from the canonical energy. So I've taken a quote from a footnote in this paper from 2016. It is an interesting question whether the conservation law satisfied by the canonical energy can be directly related to the two conservation laws presented in this paper. Okay. What's this crucial conservation law? So it's set up in the double null formalism, and it lives on a characteristic diamond on the exterior of Schwarzschild. So we have a conservation law that says that the fluxes on this outgoing cone and incoming cone are equal to the fluxes on this incoming cone and outgoing cone. Now these fluxes occur at the level of linearized metric and Ricci coefficients. So this chi bar and chi, eta and eta, these are linearized Ricci coefficients, and we have some linearized metric coefficients appearing in this capital omega 1. Okay. So it has some good terms which are positive, but it also has some terms that look like they're going to be difficult to deal with. So coercivity is still opaque at this stage, but I'll come back to this later. It can be resolved. Right. So let me address the question of whether this is related to the canonical energy. So this goes back to work in my PhD thesis. I sat down and I computed the canonical energy in double null gauge on a characteristic rectangle like this. And the expression is rather horrible, as you can see. So, I mean, it obviously satisfies a conservation law because it arises from a divergence-free current. And this is the expression that one gets. And okay, you sit and stare at this and lose a bit of hope. But if you stare very carefully, you see some of the terms that arise in Hosegel's conservation law are also arising here. So it looks like there is some relation. So what's the resolution? Well, is it related to this conservation law? The answer is yes. And the trick is essentially to spot total derivatives. So if I add and subtract the same quantity on the sphere here and take a v derivative and a u derivative, I can push terms onto the fluxes, onto each flux. So if you do this, and this is a theorem pulled from my thesis, you can show that the canonical energy is equal to, so the canonical energy flux through an outgoing and an incoming hypersurface are equal to the flux that Hosgel writes down on those respective hypersurfaces up to a boundary term on the spheres in the corners. Okay, and those cancel because they come with the opposite sign. So you can show that from the canonical energy, you can deduce this Hosgel conservation law. So I've written it again here. All right. So what about coercivity? So I'm going to present a slightly simplified argument that I deduced with Marius and Elena when we were looking at the Reisner-Nordstrom case. I'll also outline the argument that Gustav and I had, and he had in his original paper for coercivity. But it turns out you can simplify these conservation laws quite considerably if you stare at them long enough. So each flux can be simplified to a shear term and this torsion term and a boundary term. Okay, and I've written the boundary term in a suggestive way. So the first line is good because it's positive. Now one has to just deal with boundary terms. I've written the explicit expressions for x and lambda here. They're not especially important. It's just for concreteness. Something to note, and I've sort of swept this under the rug so far, is about residual gauge freedom. So double null gauge doesn't completely fix your gauge. There are residual transformations which result from refoliating your cones and refoliating the spheres, um, which one can use to your advantage. It turns out when the fluxes are written in this form, the first line here, these are gauge invariant under transformations adapted to their respective cones. So if I refoliate this outgoing cone, this is actually gauge invariant. Okay. So how does the argument for coercivity go from this perspective? Well, the first step is the same as the first step is the same throughout the years. It's been the same that Gustav, sorry. The original argument goes through, it's a push to null infinity. I take this incoming hypersurface and I push it to null infinity, but I need an appropriate notion of extendability. So the boundary terms that arise, I'm going to write it in a special way, they decay under a suitable notion of asymptotic flatness. So the appropriate definition that comes from Gustav's original paper is that a solution is extendable to null infinity if the following quantities have finite limits as you push v to infinity along each fixed u. Okay, the list I should write for the whole system, but I'm pulling out the relevant quantities here from that list. So under a suitable notion of asymptotic flatness, R lambda is the finite quantity, and it turns out that x is the finite quantity. So this term decays, and this term decays since I have a 1 over r. So it turns out that if if I push the incoming flux to null infinity, I get something that's coercive automatically. So it's just the outgoing flux that one has to deal with. Now, you may wonder how realistic an assumption this is to make, but from the Firmus Hosgel and Rodniansky in 2016, one can always normalize my initial data to satisfy this. And these rates, moreover, propagate along null infinity. Okay, so what about the incoming cone? So the argument, sorry, the outgoing cone. The argument here has changed over the years. So the original coercivity argument depended on gauge transformations. So in Hosgel's original work and our work in 2024, we used the residual gauge freedoms that were adapted to the outgoing cone. So the key quantities that we used were this omega trace chi, the expansion of the outgoing cone, and we noted that the shear was gauge invariant under this quantity. So let me go back to the original go back to Gustav's conservation law. Why is this useful? So if you look at this outgoing flux in 13, the shear is gauge invariant under such a transformation. And I can use the expansion gauge transformation to set these last two quantities to zero. So I'm left with one other term. It turns out that if I set the expansion to zero, Marshall-Dury's equation tells me that this middle term is also zero. So you get something that's coercive, but in the wrong gauge. So something that Gustav noticed was that these fluxes were gauge invariant up to boundary terms. And you can essentially see this from the simplified form that I presented on this slide. You can see that these two terms, I told you that these two terms were gauge invariant, and you're left with the boundary term. So it's gauge invariant up to boundary terms. So the original argument for coercivity of the outgoing flux was to look at the difference of to write it in a gauge where the expansion vanished and relate it to the original initial data gauge and deal with the boundary terms that arise from this transformation. And it turned out that that was possible. However, in the simplified setting, one can spot a miraculous transport equation. So it turns out that, and I wrote it in this particular form in the suggested form to highlight this, it turns out that the outgoing flux can be made manifestly coercive. So this term here cancels with this term at the future sphere cancels with its initial data term since it's transported along the outgoing cone. So you end up with something manifestly coercive on the outgoing cone. If you push to null infinity, you get something that's coercive. So you end up with this nice coercive estimate from the modified, albeit modified canonical energy. Okay. So there is a failing here, which is interesting if anyone is wanting to explore, is that the analogous argument where one pushes to the horizon first and tries to make the incoming flux manifestly coercive fails. The signs conspire against you, and I've thought about this for a long time, but I cannot make it work. So there's something to try and understand here. It could be that the structure of null infinity is essential here. Okay. So how far can you push this? I've only got a partial energy boundedness result here. How far can you push this? Well, it turns out that you can get control on the Tchaikovsky variables from these conservation laws. So this is the main theorem from our paper from 2024. If you give me a smooth solution to linearized gravity on the Schwarzschild exterior, we can estimate in terms of uniformly bounded initial data all tangential derivatives to the outgoing cone. We can actually get all derivatives just because there's a Bianchi identity for this of alpha, and we get all tangential derivatives of alpha bar, although with some degeneration, although one might expect that if you invoke the Tchaikovsky equation and do a redshift estimate, you can improve this. So how does this work? So I'll give you the essence of it. You can commute these conservation laws with the symmetries of the Schwarzschild spacetime. So with the SO3 killing fields and DT. So for example, if you wanted to get control over alpha, you would look at the commuted canonical energy conservation law with DT. Okay, and so you get control over DT of the shear. You have this already appearing in the first canonical energy conservation law. It turns out with some transport estimates, you can get control over the other quantities as well. And what's nice about this, and why I think this is really well adapted for studying higher dimensions, is that it doesn't require a transformation to the Reggie-Wheeler equation, and it doesn't even require analysis of the Tchaikovsky equation itself. So you don't have to invoke any decoupling, for example. This just comes through figuring out a hierarchy that sits in the system of linearized gravity. Okay. I have 15 minutes, is that right?
Yes.
Okay. So let me skip through putting Reisner-Nordstrom and double null gauge. You can put, let me just say, you can put Reisner-Nordstrom and double null gauge and also do the linearization around Reisner-Nordstrom. You have extra quantities associated to the Maxwell field, which you have to decompose with respect to this null frame. So you have this rho f, sigma f, beta f, and beta bar f. And you have a coupling between gravitational electromagnetic quantities through Q. So you can see here that this is after linearization around Reisner-Nordstrom. You have coupling of the Maxwell quantities to here, for example, is a linearized connection coefficient. And the same thing happens in the linearized Bianchi identity. So one has to really deal with explicit coupling. However, the conservation laws, and this is what Marius and Elena and I figured out in 2025, go through quite cleanly. So the modified canonical energy conservation law on the exterior of Reisner-Nordstrom can be stated in quite a clean and simple form with a slight modification from the Schwarzschild case. So you get three extra terms here in the middle. So the Schwarzschild conservation law is just these last two. You end up with three extra terms for the Maxwell part, which all contribute positively. The issue that I'll talk about is with the boundary term. Okay, so how does the argument go here in the Maxwell case? So the outgoing, sorry, pushing the incoming flux to null infinity goes through just the same as in the Schwarzschild case. It turns out that these terms here decay sufficiently rapidly so that you get something coercive when you push to null infinity. The issue arises for the outgoing cone. So we have a partial result for this. So I'll try and explain where this comes from. So we get a coercive estimate for Q less than or equal to root 15 over 4m. And this essentially arises from these two terms here. So if you remember in the Schwarzschild case, this term was transported, so you could cancel the future sphere term with the initial sphere term. Unfortunately, in Reisner-Nordstrom, this term is no longer transported. It actually it produces essentially this rho f term that sits here. So one might hope that you can do some estimate and recover coercivity up to and potentially including extremality, but this fails before extremality. And the reason is the reason one can spot is the reason one can see through is the following estimate. So if you compute from the linearized equations the dv of this square here, which tends to this red term here, you can see that it produces this rho f term. So I can add this on, I can add 0 effectively in this form to this conservation law and try and cancel this term in red. Or more naturally, what I can do is I can add this quantity on the right-hand side to the flux and get a quadratic form in x and rho f. And in the boundary term, I can get a quadratic form in x and lambda. Okay? And if you look at Sylvester's criterion, which gives you a set of necessary and sufficient conditions for positive definiteness of a quadratic form, you find that this works up to and including works for charges up to and including root 15 over 4m. Okay? And so here there's work to be done. It's unclear whether one can produce an estimate which absorbs it into, say, some of the other Maxwell terms or some of the other gravitational terms. But in some sense, we have an optimality result in terms of how much can be absorbed in terms of this rho f term. Okay. Again, one can push this quite far and gain control over the Tchaikovsky quantities, which there are now 3 of them for Einstein Maxwell around Reisner-Nordstrom, and this was identified by Georgi in 2020. So you have combinations that are gauge invariant in addition to alpha and alpha bar, which satisfy Tchaikovsky type equations. And you can again gain control over all tangential derivatives along the outgoing cone in terms of a uniformly bounded initial data energy. Okay, so everything goes through up to, but not including charges of, there's a typo here, this should be root 15 over 4. We lose the equality here because at the equality of root 15 over 4m, we lose control over many of the quantities. So we can't push the hierarchy we constructed. Right. So let me talk a little bit about work in progress. And I've thought about this for many years and it's still in progress. So what about higher dimensional Schwarzschild? So I think it's particularly well adapted, the canonical energy method, to think about higher dimensional Schwarzschild because it doesn't rely on any decoupling of the Tchaikovsky equation and it doesn't require transformations to some Reggie-Wheeler variable. So the conservation law can again be written in a fairly simple way. So the conservation law looks like it does in four-dimensional Schwarzschild with an additional term which includes the Ricci curvature of the perturbed spheres. And the boundary terms are almost exactly the same up to dimensional factors. It turns out that if you make a suitable notion of extendability to null infinity, the incoming flux is coercive when you push it to null infinity. And what I think is the suitable notion of extendability to null infinity is taking the values in 4 dimensions and raising them by half a power for every dimension you increase. These rates propagate along null infinity. The issue that arises again, the outgoing flux. So as happened in Reisner-Nordstrom, the transport of the natural quantity in higher dimensions fails. So it's proportional to the double divergence of the shear with a dimensional factor which makes it 0 in 4 dimensions. So if the shear is divergence free or it's constructed from a covector potential, this vanishes. So you have a transport equation. There's another additional issue, and it's the reason why I didn't write it in any suggestive form on the previous slide with a difference of squares, is that this x quantity, as I've written it in higher dimensions, doesn't have a regular limit towards null infinity. So there's 2 issues with the boundary term that one has to deal with. Another puzzling issue is also that, well, is this mixed term between the Ricci curvature of the perturbed spheres and the shear. So you can exchange it doing this trick with total derivatives to a term which is a quadratic form in the linearized metric on the sphere and its angular derivatives. This is positive, definite when it's sourced when this linearized metric is transverse or sourced by a covector potential, but is negative definite when sourced by a function. So if you construct it through 2 angular derivatives of a function, it has the wrong sign. So there's something to be understood here in terms of decomposition. There is some hope that one can rectify this with an additional conservation law, which is novel in more than 4 dimensions. I won't present it here. It's also very complicated and not particularly enlightening, but it does give control over this perturbed Ricci curvature in higher dimensions, or it could give some control, I should say. It does. I've not proved it does. Okay, so that's the status of the higher dimensional case. It seems promising, but there are lots of pitfalls that one has to deal with. So what about the outlook for the canonical energy? Well, an interesting question is looking at axisymmetric linear perturbations of Kerr, and this should yield to this technique, but one maybe has to be a little bit careful about the decomposition that one uses. I, at some point, did the computation in double null gauge, and it gives a very complicated expression, which is difficult to read off coercivity from, but maybe one can find the correct gauge invariant variables and write it in this way, as I did in the Schwarzschild case. It's certainly an interesting problem. The process that I've highlighted so far very much exploits this notion of extendability to null infinity. So I've thought a lot about trying to push to the horizon first and have failed in the attempt. So it seems like this definition seems somewhat necessary to make this work, but not to say that one can't push to the horizon first, but it's an interesting problem to explore. And relatedly, what can one do with different asymptotics? If you took Schwarzschild ADS, what can one do in this case? Anyway, I think I'll end here and thank you for listening.